Okay, I'll start now. There we go. So on a Moodle problem, how am I going to get this answer? Because in Moodle, look, it's a little bit, oh, that's the wrong one. No, it's not. That's right. So on a Moodle one, I'm not actually, I'm graphing it, but I'm trying to pick the correct graph, right? So I don't even have to even almost go through the whole process. If I just know the values of A, H, and K, I can use that to determine what the correct graph is, can't I? So let's do this one. What are the values of A, H, and K? So there's my function. You tell me, what's the value of A? A is 4. Okay, how about HK? Negative 1, 4. Okay, so then we know that the vertex should be at negative 1, positive 4. So it should be right there, shouldn't it? Okay. Is that the right graph? It's not the right graph, though, is it? Because we're multiplying the normal heights by 4. So normally I would go over 1 and up 1, right? So this time I'm going to go over 1 and up how far? 4. 1 times 4 is 4, so I'm going to go over 1 and up 4. So my graph should look like that. Yeah, right? So I just got to find the one that matches that pattern. So I know these coordinates, those coordinates are negative 1, 4. So let's find it. No. Oh, look right there. How about that? Right, so there's what we want. What do you know? Okay? Okay, so then the other thing that I'm going to do is I'm going to reverse that process on you. I'm going to say, now I'm going to give you a graph, and I want you to tell me what's the function that goes with that graph. To me, this is easier, right? Because all you have to do here, I can, by inspecting this, I can pretty easily look at this and say, okay, well now, what are H and K? So what are they?
Negative
3. 3 and 2, right, are H and K. So H equals 3, K equals 2. Okay, now what about A? So normally we would be going through that point, wouldn't we? So normally we're going up by 1. What are we going up by here? 5, right? Okay, so I'm going up by 5. So then we know that the normal value, right, 1 times A must equal what we end up with, which is 5. Well, if I solve that, that's pretty easy to solve. What's A equal to? 5. So now I've got this, I plug those in and I'm done. So my answer is f of x equals 5 times the absolute value of x minus 3 plus 2. Done. Right? Just kidding. Okay? Just like you said. Okay, so for today, so we're going to take one small step forward here. We're going to introduce quadratic functions. So you guys are going to practice the transformation stuff. For today, we're going to go really small step. We want to just know, how is it that we can graph a quadratic function? If we're given a quadratic function, how do we deal with it? There are going to be 3 different ways, only 2 of them for a while. But in this unit, there's 2 ways we're going to write quadratic functions. The next way we write it in vertex form is going to be more convenient. But we've got to know how to deal with standard form also. Okay, so what is standard form? Standard form for a quadratic function, that should say function, not equation. Is this. F of x equals a x squared plus b x plus C. Okay? So for, just like we had an A and an H and a K in the previous example that we looked at, this time our parameters are A, B, and C. I can create any conceivable parabola by just dialing in values for A and B and C, right? Unfortunately, A and B and C are not very useful for graphing. It'd be much better if we could write this in a form where we had H's and K's, which we will after we get back. And we'll do that next year, how about? We don't want to deal with that this year. We'll do that next year. So when I say next year, though, I mean like in 2 weeks, right? Okay, so a couple things about this. So we gotta look at the anatomy of a parabola first of all. We know that anytime we graph a quadratic function, we get a U-shaped curve called a parabola, and we saw that in our list of parent graphs, right? Y equals x squared is just a really simple parent graph, simplest possible parabola. Some things we got to know though. If A is positive, then that means the parabola opens up. If A is negative, then the parabola opens down. It turns out that the A in standard form, conveniently, is exactly the same thing as the A in vertex form. Tells us the same information, right? So in this case, this one, A must be what for this graph? Gotta be, well, it's, I mean, A is, actually, we don't know what A is as a number, but we know it's negative at this point, right? A is just, it's negative because it opens down. So what are the parts of a parabola then? If we want to look at the anatomy of a parabola, we know that one part of it that isn't even technically a part of the parabola, but it's very useful, is this axis of symmetry. So the axis of symmetry is just that vertical line that passes through the vertex. And it's an axis of symmetry because you can see it displays the symmetry of the parabola. The right part is a reflection of the left part, isn't it? Right? And so once again, we love using symmetry in math. Symmetry in math makes things much, much easier. We're about to do some stuff in calculus where we're doing curve sketching. We're going to do an analysis of these functions based on calculus and pre-calculus stuff. And what the students are going to have to do is I'm going to give them a complicated function, and they've got to be able to make an accurate sketch of it. But part of the process for them is if they can find these different kinds of symmetry that make it easier to do, then they can cut their workload down tremendously because it's a time-consuming process. You got to build these big tables that take up a whole page. I mean, it's a process. We do that in other ways too. Like I'll give you another example of symmetry. Sometimes we only think about symmetry as being maybe a mathematical visual kind of thing. And you're used to seeing that. If you go back to geometry, you guys for sure talked about symmetry a little bit, right? Like if I draw say I draw a weird shape. I'm going to draw this shape. So this is going to be a strange one. Some strange polygon. So that one. Does that strange polygon have any symmetry? What kind? I see John shaking his head. Yes. Nodding. Okay, good. It's bilateral symmetry. Perfect. So we can see that this one, if I were to draw a line of symmetry right there, it folds along that line, doesn't it? So this has reflective symmetry over that line. Okay? Now tell me, does this shape here have more or less symmetry? What do you think? More or less? Is it more or less symmetric? More symmetric. How come? So are there any lines of symmetry here on this one? Yes. Yeah, a bunch, right? So one of them would be right there, wouldn't it? Where's another one? Okay, I could also fold it along that line. Any others? Diagonally there and diagonally there. There's tons of folding symmetry. There's even other types of symmetry here. Can I rotate this one less than one full turn and have it line up with itself? No, I don't know what that is, some kind of crown. That one has no rotational symmetry, does it? But this guy does, right? If I were to put a tack in the middle of this piece of cardboard and rotate it, I could rotate it through 1/4 turn and it would line up perfectly, wouldn't it? Or I could rotate it through a 1/2 turn and it would line up perfectly. Agreed? So this one has a lot of symmetry. Well, what's a shape that has even more symmetry? Oh boy, a circle. if we look at a circle, how much symmetry does a circle have?
All of it.
It's effectively got infinite symmetry, doesn't it? Because I could, how many different lines of symmetry could I get?
All of it.
Oh my gosh, anything that goes through the center is a line of symmetry, right? So that's a line of symmetry, that's another one. I could take this thing and I could just budget through an infinitely small angle and create just slightly, or I could slightly twist this line and I've got another line of symmetry, right? What we talk about in calculus is something like taking the limit of that as the size of the angle goes to 0. If I did that, I'd end up with an infinite number of lines of symmetry. I can do the same thing with rotation, right? If I put a tack in the middle of that circle and I spin this thing, any angle I spin it through always lines up with the original, correct? So if I spin it through an angle that approaches being 0, I'm going to have an infinite number of different angles I can use. So it's infinitely symmetric, right? Okay, what about time symmetry? You never thought about that probably, right? But you can even do things like in physics we talk about, and this is bizarre, but almost every equation that we use in physics, every model that we use to describe the universe is completely symmetric with respect to time, which is bizarre. And so it begs the question, why does time go forward and not backward? Could time go backward? Could there conceivably be a universe where it wasn't a cause and effect universe, it was an effect and cause? Could there be a universe where things like, how about that one, right? Because all the laws of physics work equally well in both directions. So you're used to seeing things like if you drop a coffee cup on the floor off and push it off the table, it shatters into a bunch of pieces. But in this other universe, could the coffee spontaneously gather up into the glass and the glass come together and land on the table? Bizarre, right? And so it's, yeah, it would be. And it turns out that that's probably, in physics, we realize that's probably not possible because of, but we had to think really hard, and it was a long process before we came to the conclusion that that probably can't happen. Probably there has to be a cause and effect, and it has to do with entropy. There's a law in physics, the law of thermodynamics, first law of thermodynamics tells us that entropy always increases, so that the randomness of the universe always tends toward maximum randomness. And so it's, you don't really see things naturally occurring where the level of order, it goes from being disordered to ordered, right? There are some small instances of that, but taken as a whole, the universe doesn't do that. The universe always tends to become increasingly disordered. Things tend to spread out. So honestly, it's a good defense for when your parents tell you to clean your room. It's, just why? I'm just fighting entropy. It's inevitable. Things are just always going to get more random and disordered. So it's a losing battle. Why fight it? It might not work, but you can try. So anyway, to exhibit though this other kind of symmetry, this time symmetry, this is kind of interesting. You got to think about this little mind experiment here. So let's say if we were a little thought experiment. So let's say we're going to film. I'm just going to take a ball, I'm going to throw it up in the air and catch it. Okay? We're going to film that. Okay? So if we film, we all know what that looks like. The ball starts off going pretty fast, and when it gets up to its apex, it's where its velocity is 0, and then it returns back, right? So if I showed you a video with that, would you know the difference if I had done, version A is, I filmed this thing and I'm just showing you the complete video of the ball going up in the air and landing in my hand. Version B is, I only film the upward trajectory, and then I just reverse the direction of the video and play the reverse of the upward journey.
Yes.
So I never actually filmed the downward journey. Could you tell the difference?
Yeah.
You couldn't.
I guarantee I could.
You couldn't tell the difference. If a person were a good video editor, you couldn't tell the difference.
But it's all like the face and the eyes. Like you wouldn't, nobody like throws a ball and then like just does it so perfectly. It's gonna look different as it comes down. 100%.
Okay,
you can't
so
argue.
but we're gonna
That's
take,
what I'm saying.
so we'll take that part out. We'll say we're not even filming the person.
Just
You're only
like
gonna film it as the ball goes up and then it comes down, and my hand's not even in the video frame.
Well,
So the answer is, you could not tell the difference. There's no perceptible difference between the two. And in fact, if there was a vacuum in the room so there's no air resistance, there would be physically no difference, right?
but wait, I still got a problem. Because if it's just a hand, right, and you throw the ball, you don't catch the ball the same way you threw it. You know, you would tell the difference.
It's only the ball.
But you see the ball going up and down?
Yeah, you're not seeing
Oh,
you're not
that's
seeing the
fun.
hand. Okay? So if you don't see the hand, you can't tell the difference, right? And the reason is, because that journey of the ball up to the top and down back to your hand, we would say that it is completely symmetrical with respect to time, right? The journey up takes the same amount of time as the journey back down. And really, what does time do in physics? All time does is it distinguishes one moment from the next. So in physics, we talk about everything is an event. So the event of the ball leaving your hand would be marked by an exact time. If we all had synchronized watches, we could say, okay, it happened at exactly this time. And we could even say where the location was, right? We could say it's exactly at that location right there. So if you combine that instant in time that we all agree with, and that location, that's an event, right? And then there's an infinite number of events as the ball slows down. The only important ones are probably when it leaves our hand, when it gets to the top, and when it returns to our hand. But all the events in between leaving my hand and getting to the top, those events are completely mimicked in reverse by the journey back down, right? And so that it's completely symmetrical with respect to time. It's not even a physical symmetry, right? So symmetry is a big deal. I mean, we really want to harness that as much as we can in physics. And there's even some other, like, extremely bizarre symmetry that physicists would talk about, like string theory. And someday we'll talk more about string theory. But string theory is kind of the leading candidate for the theory of everything. It unifies all our understanding of physics. String theory, the math is incredibly complex. There's probably only 20 or less people on the earth that can even at this point understand the math. It's that complicated. I mean, they're literally the smartest people in the world. String theory, it says that the universe, instead of having just instead of just three dimensions, like we're used to 3 dimensions, right? Like we can describe, there's only room for three different directions in our universe. You can go left, right, up, down, forward, back, and that's it. Right. Beyond that, there's no room for any other directions. Though that's enough to describe everything. Say it again. Well, but diagonal is a combination of left, right, up, down, so that doesn't count, right? There's no other. And to be more specific, in order for it to count as well, how do I say this? In order for it to count as a dimension, like when we say 3D, we live in a 3D universe. In order for it to be 3D, all of the different directions that we draw have to be at right angles to each other, right? So let me show it to you this way. I'm going off on a tangent, but this is kind of interesting.
This is lit.
So there's, in 2 dimensions, we have an x-axis and a y-axis, right? It's 2 dimensions because there's only room for 2 different directions, 2 different axes that are at right angles to each other, right? Now, if I introduce space, instead of 2D, we go to 3D, then there's another one that comes out of the board, right? So we call that the z-axis. And you can see that the z-axis is perpendicular to the y-axis. That direction and that direction are perpendicular. And the z-axis is perpendicular to the x-axis. That direction and that direction are perpendicular. And we already know that x and y are perpendicular, right? So we'd say that those are all mutually orthogonal, is our fancy math word for perpendicular. There's only room for 3 mutually orthogonal directions. Now, in a 4D space, there would be another one somewhere. We don't have room for it, right? Okay. But in our universe, there were 3 extended dimensions. Well, string theory says there's an additional 7 tightly wound up dimensions on a very small scale that we don't even see because they're kind of curled around on a very, very small scale.
Are they curled?
Well, it's bizarre. String theory is pretty bizarre. And they would explain why gravity works and things like that, right? But in string theory, the reason I bring this up, these thinkers, these brilliant physicists that think about this stuff, and they develop the mathematics, there's a weird kind of symmetry in that. They can do these little 7-dimensional spaces in this 11-dimensional landscape of string theory. They can do these 7-dimensional spaces called Calabi-Yau spaces, and the math is just it's so brutal. But they find these symmetries in there, and by harnessing these symmetries, they can understand the way that why gravity does what it does, why electromagnetism does what it does, why light does what it does. String theory actually points to all these mechanisms. Very bizarre, but it seems to be working. Yeah.
Just somehow in some way get that dimension right with everybody in 2D.
Well, not in our universe, but in an alternate universe, sure. It's possible. Mm-hmm. Okay, so anyway, back to back to our stuff here. So this is, and I want you just to see here, because this is why sometimes it's easy to lose sight of math. It's just, it's pretty dry sometimes. But this is all just one step on a path of bigger stuff, right? I mean, in order to extend this, to think about some of the things we've talked about, it all really starts here. And in fact, like if you were going to look at, we talked about that ball being thrown up in the air. If I were to graph the height of that function, if I were to graph it on instead of the xy plane, let's do this. I need to put my tangent. I didn't plan on going on this big tangent today, but it's the way it worked out. So if this is the time axis and this is the height axis for our ball, the path of the ball up in the air, okay, let's do this. We can arbitrarily set any time to be time 0 that we want to in physics, right? So like if I set time 0 to be right now, then you guys walked in the door at about, the time would have been about minus 35 minutes or something, right? What's the minus mean? It just means 35 minutes before time 0, right? Is time negative? Well, I mean, in that sense, yeah, it is. A negative time just means a time before what we're calling time 0, right? So if we call time 0 the point when the ball is at its apex, what does the graph look like of the height of the ball as a function of its time? I'll tell you what it looks like. It looks like this. Right? Only it never goes below the t-axis because that's where we release the ball, right? But it looks exactly like a parabola. And what's the line of symmetry? The line of symmetry is the line t equals 0. How about that, right? I mean, it's so you can see that this really does have applications in like real stuff, right?
That's cool.
Okay, that is kind of cool, huh? So when are we out of here? 2 minutes. 2 minutes. Okay, so we got to just fill in a couple things, and we'll deal with the stuff after the break then. So we said this is the line of symmetry, right? So the axis of symmetry, the formula is really simple. What's the equation of a vertical line? It's always just, isn't it just x equals whatever the x-intercept is, right? So for us, it's always just going to be x equals whatever we calculate that x value to be. And here's the formula that we use. It's very simple. The formula is just negative b over 2a. It always works. What are the a and the b? They're just the coefficients in our standard form of a quadratic function, right? So for example, if I have the quadratic function something like how about like that one? A is just whatever's being multiplied by x squared, so it's 1. B is whatever's being multiplied by x, so it's negative 8. And C is the constant, so it's 9, right? Okay, so that's how we can always determine what the axis of symmetry formula is. Well, if that's the formula for the axis of symmetry, then what's the x-coordinate of the vertex going to be? That, right? Isn't the vertex always going to be on the axis of symmetry? Right? That's the axis of symmetry has to split it in half, so it has to go through the vertex. So whatever we get there becomes our x-coordinate, right? Okay, we'll leave it off there.